we hear a lot these days about the ever-increasing number of cars on the road and all the things that cars are putting out, whether it be carbon dioxide, sulfur dioxide, all the emissions that you hear about. Even now they're talking about the particulates from worn tyres and brake pads, and the effect that those are having on our cities. But there's something else that modern cars are putting out that people don't tend to think about a lot, and that's data. Modern cars are packed full of what they call ECUs, which are small computers that manage different aspects of the cars, and these produce streams and streams of data that you can then process and understand what's going on in the car and where that car's been and what state it's in. And this is incredibly useful information for manufacturers in order to keep iterating on their designs and making sure that the vehicles they're producing are safe and reliable. And here at MongoDB, we help a lot of manufacturers manage that data, and we've got a number of well-used use cases and architectural patterns for building systems that manage automotive data. And I think today what I wanted to do was show you what that kind of looks like with some synthetic data that I've made up, and how we can use that to derive insight on car journeys and the state of vehicles. So I'm going to flick back over to the laptop because I can't do this whilst I'm driving, obviously, and I will see you in a few seconds. So we built a whole bunch of blog posts based around how to deal with time series data, and the second blog post here, which you can access on the MongoDB blog, talks about how we can design a schema that's going to work for this particular type of data. And there's a number of different scenarios that you can use for this. So the first scenario that we can discuss is essentially it's kind of a naive kind of porting from the relational world, where you have effectively one row per sample or one row per packet of data, and this obviously in MongoDB is expressed as documents, so you have one document per sample. Now the problem that you see here is that when you've got this kind of repetitive row by row, document by document sample, you end up with a lot of wasted space. I mean, this particular field here, symbol MDB, is duplicated in every single record, and you don't need that. Why would you need to store that in every record? So you have to think a little bit smarter than that with time series data, and MongoDB allows you to have the flexibility to model this data in lots of really interesting ways. So scenario 2, which is a lot more interesting, is where we start bucketing this data together over a period of time. So we can say, okay, if we're getting vast volumes of data in and we're having hundreds of thousands of records per minute, we can say, let's just store a whole bunch of records per second, and then every second will flow over to another document. For some use cases this might be different. You might say, okay, maybe it's per week that will flow over to a different document, or however you want to structure it, but the idea is the same. You can start bucketing together all this time series data, so you don't need to repeat a lot of that metadata that comes with every packet. And the blog post goes on to discuss some of the savings that you get in terms of the number of documents and things like that. So you can see here, if you use the naive, one row per sample kind of methodology or scenario, you quickly end up with hundreds of thousands and millions of documents. Whereas if you're bucketing over a period of time, then you can keep this document count relatively low, and that means that you get much more performant queries out of it. Likewise, the size, it speaks for itself. You can save a lot of space in the database by starting to bucket all this and not having to store every time all the different permutations and the duplicate data that you end up with. And it goes on, and this is a good model, but it's not quite right for what we want. This kind of time-based bucketing is useful when you have data that is provided regularly. Maybe a sensor sends you a packet per second, or there's a regular cadence to the data that comes in. What we've got with time series vehicle data is we've got cars sending us a packet of data at the end of their journey. And this isn't over a large sample. This could be over aggregate, quite average, but for any one vehicle, it's not a regular transmission of data. It's whenever they finish the journey. So we've got another scenario here, scenario 3, which is size-based bucketing. And here what we've got is the idea that you can create a bucket, and you can predefine how many samples you want to add into this bucket. So you could say, okay, I'm going to limit the bucket as they have in this blog post to 200 samples, and then when I hit 200, I'm going to overflow to a new document, and it makes it very easy to do this kind of analytics on the data. You could obviously, since the 200 is as I say, is arbitrary. You could use 10 documents, or 10 samples per document, or you could use 2,000 samples per document. Whatever's useful, given the frequency of the data. And this is the kind of pattern that we used for looking at this kind of vehicle data. So if I skip over now to some code, this is basically a little application that I wrote, a little script that I wrote in Ruby that's just going to kind of help us visualize some of this. And essentially what it does is, up here I have a function which goes and creates a fleet of vehicles. It's going to create a fleet of 100,000 different vehicles, and essentially give them a random starting place and some random data to start with, and then randomly and over the period that the script runs for, it's going to go and take each of these vehicles for a drive. It's going to go and take it for a spin. It's going to put some miles on the clock, and update its coordinates and things like that. And then it's going to once that journey is over, it's then going to send a packet of data to our server, to our MongoDB instance, so that we can catalog what it's been doing. And the piece of code that's going to do that is this update statement here. And essentially the update has a particular argument appended to the end of it, which is called upsert. And this is the mechanism which is going to allow us to overflow from one document to another once the counter has been updated. So we contain within the document itself a field called update count, and we have specified what we consider to be the maximum updates per document, and we match the update. We say, okay, go find me a document that matches the vehicle identification number that we're interested in, the VIN, and see if you can find any one of the documents in the database that matches that VIN that is currently has an update count less than the maximum updates per document. If you can, just go ahead and update it with the latest journey details. If you can't find one that has any space left in that document, i.e. the update count matches the maximum updates per document, then go and insert a new one with the update count set to 0 or set to 1, which is it. So that's kind of what the script does. Let's go and have a look at some of the data. So if we pop over to MongoDB Compass over here, you can see this is the collection that I've built. There's about 1.2 million documents in this collection, and it's very noddy kind of data sample. You've got, I haven't specified any particularly interesting vehicle identification numbers, VINs, but they're all there, and each one of these has an array in it which contains a bunch of sub-objects which describe particular trips that this vehicle has taken. So this, in this particular document, the fourth trip, because it's indexed off 0, was of 16 miles, and it particularly had these statuses at the end, and the last coordinates that we saw it at were these ones. So this allows us then to kind of be very prescriptive about how we're storing this data, and we don't need to duplicate a lot of the original data, like what the model of this car is and what the market that it's operating in and other things like this, which we get every packet, but we don't need to duplicate because they never change. So we're just able to update and be very efficient about how we update that data. So how would you go about querying it? Well, the other thing to point out is that just for the sake of efficiency, because we have this incredibly flexible document model, one of the things we can do is just keep some of the really pertinent information, the stuff that we know we're going to query, we can keep that up at the top level of the document. So although we can do some really interesting things by going through all the trips that this vehicle's ever done and averaging out, if we just want to find out what the mileage on the clock is, we can keep that updated in the root of the document here, and it makes it very easy to run queries, and we can just keep stuff that we need to access very quickly, that's useful for the use case that we're working with this data on. We can keep that at the top level, keep that updated, keep that fresh, but still store all the historical data for that vehicle so that we can then access it if we need to. Let me kind of show you what I mean by that. So the next thing that we can do is utilize the MongoDB's aggregation framework, and we can say, okay, let's just explore some of this data, and let's say maybe we want to do a group by, for instance, that's going to allow us to kind of slim down some of this data into or kind of aggregate it up into different kind of values and get some insight out of this. So we can say, right, the ID field, for instance, I want to be based on, say, the model. So I'm going to go put that in quotes here, model, like that. You spell that right? Yeah, yeah. And I'm going to call the field maybe average miles, and my accumulator is going to be a dollar average operator, and the expression is going to be, say, dollar something like that. Okay, so what we've got now is a calculation by vehicle type of what the average miles is. Now, on its own, that's interesting. We've got quite a wide range of vehicles here, but what I think is more important is that we just add another stage here quickly, and we can just sort that. So we can say the field that we just created is called average miles, and we can specify a sort order of -1 there, and that's going to show us the Range Rover has done on average the largest amount of miles of any of the cars in this data set, and obviously the data is completely random, so there's very little differentiation between any of these. But then rather than model, we can say, okay, let's have a look at maybe if we go back up to the top, we can go to the market, say, we can look at maybe the sum of the Odo now, and we can say, okay, for these different markets, and we can order it by it's still sorted by the in fact I'll call this rather than average miles, I'll call it now total miles. That makes more sense. Total miles. So the total miles for vehicles in England in this data set is nearly 1 million miles, like 916,000 miles, whereas China comes in second there with just over 900,000. Let me slide this across. You can see the different territories here. So very easily I can do real-time analytics and aggregations and understand insight into the data based on the ability to do these build these pipelines very quickly. And this is running on a data set of 1.2 million records. So the next thing we can do is we can go and say, okay, well, if we've got that data, let's just have a look at, let's explore what that looks like, start querying into it a little bit. So if I go to the schema view now, I can hit analyze schema. And here we are. So what it's done now is it's looked through that data set, and it's pulled out the distribution of all the different fields that we've got. So we can say, okay, here are the market for these vehicles. The largest market is England. The minimum is in USA. The models are, the Range Rover Evoque is the least populous model in this data set, whereas the Jaguar I-Pace is the most popular. And there's loads of other data that we can see here in how the data is distributed around the data set. But what we can do is we can dive in here and we can say, okay, well, we know some of these cars are in the UK, so let's zoom in on that. And we can say, all right, well, you know, how many of these cars are driving around, say, I don't know, maybe in the Cotswolds. You know, we know the Cotswolds is quite a nice place. There's probably quite a few Range Rover owners there, so we can drag out a circle here around this area, hit analyze, and go and dive into that. And very quickly we'll get a result back, which is a subset of the main collection of data, and that will contain, here we are, that will contain 124,000 records out of the 1.2 million. And we can kind of dive in a little more if we want to, or we can start to look at, you know, how those how that data is distributed in a bit more detail. We can say, right, okay, of those queries, let's just say, okay, actually we are only interested in sort of in Range Rovers. There we go. So that's a Range Rover, that's another Range Rover as well. So we can select both of those, and maybe, I don't know, there's another Range Rover, so let's have that one too. A Discovery Sport. We'll say all of those ones there. Hit analyze, and now we're going to create just a kind of subset of those documents. In fact, I can edit that a little bit more and just take some of these out. Say, okay, we're only interested in these Range Rovers. There. Hit analyze, and that will come back with just a smaller number of documents. And this is running on my laptop as well, so this isn't a particularly powerful machine, so it's nice to see the queries coming back so quickly. And I can zoom in again, and I can say, okay, this time let's look at how many of these cars are being driven around here in the Cotswolds. Hit analyze, and there we go. So we're diving into the data, and every time we click on something we're creating new richer queries, and we're down to like 1065 of these vehicles. And I can even, you know, go down even further and say, right, let's just give us, you know, maybe just a couple of these vehicles. Let's dive in really close this time. And now we've only got 8 records, and we can have a look at which 8 records these are, because if I go back to the documents view now, click here, these are the 8 vehicles that we've been talking about, that we've found. And I can say, okay, let's just this time query on this VIN number alone. Okay, so rather than have this long complex query now, I can say VIN : is this one. Oops. I need to wrap that in curly braces. There we go. And there we go. So this car, this specific VIN number, this car has got 15 records, so it's done quite a few trips, and we can see, you know, each one of these is overflowed. I've set the limit at 10 documents per 10 samples per document, and if we now go back to the schema view and update that with the same VIN number, then we can dive in and we can see exactly where this vehicle's been. And this is the last known position for all the documents, but the whole point here is that we have this trips field in here, and this is the sum of the last known positions across all the trips that this one vehicle has made. So we can now see, although that data was all buried inside those arrays, because we have it for historical usage, we can pull that out and start analysing all that data there. So that's the benefit and the performance boost that you get from using some of the existing patterns for storing time series data. Hopefully that made sense. I'm really looking forward to seeing what some of you guys do with this. It's an incredibly performant way of storing data. So back in the car again. I hope you found that useful. There's a lot of interesting stuff that you can do with time series data. It doesn't have to be automotive data. I mean, this could apply very much to other types of vehicles, other types of manufacturing. Anything that's going to be producing large streams of data can be processed in the same way. It doesn't even have to be manufacturing. Things like financial services, tick data stores, all these kind of things where you have volumes of data that are coming in. This kind of bucketing approach to data allows you to be very efficient about how you store data, and MongoDB is really well placed for dealing with that. So thanks for watching. If you enjoyed the video, please subscribe or hit the like button, and I'll see you in a future show. Bye.